Today we are going to learn very important area, Butala. Very important area. So today, if you look into the contents we have covered, okay, this from the syllabus, just for your good feelings, okay. We will see up to what level we have learned this. The energy balance, first law of thermodynamics. Okay, apply first law to engineering systems means understanding this closed systems and also the open systems, what we call we are using steady flow energy equations. Okay, that is. And second law, it's about the entropy. Okay, it's about the entropy rise and all. The Clausius inequality, you have learned this. Okay, you have learned this very well, and even you managed to construct TS diagrams. Yeah, very good. And today we'll be learning part of that, maybe another one. Entropy in thermal systems, we have learned, but we need to have more understanding maybe. Steady flow energy equation to open systems. So lesson 6 is about the properties under different thermal conditions. These are for the vapor, this is your ability to read the tables, saturation and superheated property tables. We have touched this as well. We did some questions also. So you have some familiarity, and later we will do a revision to thoroughly look into this. And vapor power cycles, we came to know about this as well, and we'll see how well we have learned this. And then the gas power cycles. So that's all for the syllabus. Okay. So today I'm going to consider, okay, not to say gas power cycles, but at least before analyzing what gas power means. What gas power means, okay. So this is what today we are planning. And also, if we have enough time, we will look into some vapor power cycle analysis, okay. Yeah. So this is for your understanding. So we have 1 month to go, and we have finished this in style. Right? Yeah. So we will do some revision classes. Then this is done. Okay. So gas power concept building. Yeah. So I just put a slide here, but we will see how well this slide goes really. Gas power cycle. But first you have to understand what gas means for these power applications. Because scientists, they see the gas in different ways. Technologists, they may see the applications. So you should understand what gas means for this gas power cycle application. Then you should understand what gas power means. And later you can go for gas power cycles. So That is very important. So let me look into this now. Gas power cycles. Okay. So under this, yeah. So in the gas power cycles, okay, gas power cycle, gas power cycle. Okay, but then, so you have to have understanding about this to understand gas power cycles. Understand gas power cycles. I'm not going to explain anything in detail. Okay. So gas power cycle related gas means, of course, not like vapor power. Vapor, you know, it's liquid and gas forms together, but gas means generally, you know, the gas are compressible. Gas are compressible. Give me a second. Gas are compressible and there are gas laws. Okay. Obey gas laws. Okay. Not to say obey, but the gas laws are applicable. Yeah. Defining gas in scientific ways, there can be many things, but gas are compressible because gas molecules how to say are not attached each and are far, not to say far apart, but are not attached each. Okay, a simple wordings. Okay, so there is a gap. There is a gap. Even once collided means happy German. Once collided, double A. Once collided, again depart. Okay, again depart. Once collided, departs, not together. Okay, once collided, again departs. So once collide means hit each other. They depart. Okay. So there are that kind of things you can explore. Okay. Gas means. That's why. So they are always, these gas molecules are always detached each other, not attached. Okay, means the molecular, intermolecular bonds, inter bonds between molecules bonds between molecules. Okay, bonds between molecules almost, yeah, bonds between or among. Okay, yeah, let's say between molecules almost non-existing. Not to say none, but there are bonds. Yeah, almost none. Not to say non-existing, but extremely weak. Weak. And these bonds we call van der Waals bonds. Van der Waals bonds. For real gases. Are very weak. That's why for real gases we have for real gases let's say ideal gases first. For ideal gases, you have learned about this a bit if I'm not mistaken. For ideal gases, we consider no bonds, okay, between molecules. Ideal gases. And you have the ideal gas equation for that. We have to do some examples. Ideal gas equation we call pressure times volume is, okay, PV. PV equals nRT. We have another one, PV equals M another R. Okay, so this R, PV equals nRTR, we call universal gas constant, or UT. MRTR we call specific gas constant. It's a simple arrangement, and this T is always in Kelvin. Okay, T in Kelvin. So let me put Kelvin also here. TK. Okay, so this is ideal gas equations. For real gases, we have this van der Waals equation. I have to check the spellings. Van der Waals equation. It's a modification of modified by using the ideal gas equation. Don't worry, okay? So these are the things with gases. Anyway, the important thing is this gas molecules. This van der Waals consider these weaker bonds among gases. When the bonds are weaker, gases cannot be together. Okay, and also those are energized or excited molecules, fast, moving fast. Okay, so gas molecules, how fast? We have a question. The gas molecules move fast. This can move. Okay, move fast means yeah, let's say move fast. How about the liquid? There are intermolecular bonds that makes molecules attached, okay, attached together. So they are together means if you consider gap between molecules, we would say almost none. But in gas molecules, yes, attached together. There are intermolecular bonds that makes molecules attached together. Okay, so there can be this bondage based on the polarities and all, but anyway, you have to look into this. So there are intermolecular bonds. Okay, intermolecular bonds for gas molecules, for gas. Okay, sorry, liquid. For gas molecules move fast. So liquids, so liquid molecules are comparatively, we would say, comparatively means relative to gas, okay, are slower, okay, liquid molecules are moving as molecular clusters together, and this effect we call convection possible. Or even of course there are technologies we can use, but generally molecular clusters, convection, okay, we call convection. Anyway, I will take this word out because this is too early for you to know about convections. Moving as molecular clusters. But gas molecules moves alone. Okay? Molecular clusters means moves together. So these are the differences. I believe these fonts you can read. Let me make it a little bigger. 24. Yeah. So no matter there are complicated scientific things related to this gas, we will understand this at our levels in very simple manner. That's it. Okay, that's it. So gas, compressible. Why this is compressible? We have to know. Gas laws are applicable. Compressible because there are gaps between molecules. So somehow forcefully we can make this gap close. Yeah. So this is the reason. Are not attached. There is a gap. Even once collided, again depart. Detached each. Bonds extremely weak if they have. Extremely weak. Okay. So gas molecules move fast, move along. And there are gas laws we call. There are many gas laws, but for ideal gas, this is the ideal gas equation. For real gas, this is the van der Waals equation. Later we will know this. Okay. So these are related to modeling. Okay, modeling. So at the moment, I will keep this. Gas molecules move fast. Liquid. Now, always you can understand by learning the contrast. Contrast means some, not to say opposites, but contrast. So gas molecules move fast, move alone. Okay, move alone. Liquid, there are intermolecular bonds. They are significant. That makes molecules attached together. Yeah, so those are strong. That's why when you heat liquid and finally boiling means that is the time these intermolecular bonds are being broken. Okay, so molecules are so excited at the boiling point so that these molecules become separated and then turns into steam. More energized, superheated, almost like gas then. Okay, almost like gas. Yeah, because very energetic. Not to say almost, it is gas. Yeah, because it has the same, because molecules are apart. There is a gaps, once collide, again depart. So this liquid turns into this gaseous form. You can see, move together. Of course, there are practical ways of considering this. Liquid you can put into a bottle. You can pour. Liquid can be poured. Yeah. And also it can be somehow, yeah. You can put into, yeah, those are simply poured. Yeah, liquid. Yeah. But gases, no such thing. Okay. So you have little idea about gas now. Okay, you have little idea about gas. So I explained this in very simple way, Vidala. Okay. So also don't make those things complicated. Yeah. Don't make the things complicated. Keep your knowledge to the simplest. From there onward, you can understand this. Okay. This gas has a lot of applications. Okay. Gas has a lot of applications. Lot of applications. Gas has a lot of applications. Do you know different applications? Even nitrogen gas we call into, you know, there are a lot of applications. Okay. And also you are using in tires the pressurized gas is almost like, yeah, can you remember I explained in the class, once pressurized it has a certain solidity. So that's how this solidity or the earth nature you can impose into gas. Pressurized gas. And also inert gas. Inert means it has no reactions. Example, nitrogen. Even when you weld, maybe nitrogen you can use as an inert gas to avoid oxidation. Okay. Or even to avoid rusting, you can have nitrogen environment. CO2, there are applications. CO2 applications are there. So there are gas has a lot of applications. You can explore. Okay. You can explore. CO2, even carbonated drinks, we have CO2. Sparkling, CO2. But CO2 in combustion, we have issues. Okay. So nitrogen, CO2 issues, you can see applications and also issues. Huh? Yeah. Applications. CO2 you have applications. But you have concerns, environmental concerns. Concerns a lot. By this time you should know about this. Gas has a lot of applications. And very important, you have learned about heat pipes by yourselves. So here, finally, the gas that brings the energy to the other ends. Now, superconductor. Superconducting, of course. Once, yeah, originally in liquid forms, once energized, that energy with the gas moves in lightning speeds, reach the other end, and then release that energy or unload the energy and come back in very silent way, means in liquid forms. The gas applications. Okay. So heat pipe, superconducting. So this is actually the liquid gas combined. So this is anyway, gas plays a part of that. Okay. Liquid and vapor. Yeah. So the gas can be superconducting. Okay, yeah, with pipes. So there are a lot of applications, and gas power is one of such. Okay, gas power is one of such. In this case, as power we consider mechanical power. Mechanical power. Okay, or energy. Mechanical energy. Let's say mechanical power. So gas power means ability to produce mechanical work. So gas has this power. Okay, gas power, ability to produce mechanical work. So later we will look into the cycles. The ability to produce mechanical work. So I will make this very small. Ability to produce mechanical work. Okay. So how gas can produce mechanical work? Means move. Okay. Ability to move or turn. A load. Okay, load. Turn a load. Move or turn a load. This can be a mechanical load finally. Yeah. Move or turn a load. Move, turn, lift. Okay. A load, let's say. Okay. How gas can produce mechanical. Okay. How gas can produce mechanical. Yes. So later I will come to cycles and we will look into this. First of all, gas must have a loaded energy. Have a loaded energy. Have a loaded energy to release or transfer, we call as mechanical energy. Yeah. So this is understanding. Yeah? So we are building the concept. So gas must have a loaded energy to release or transfer as mechanical energy. We call this energized gas. Now, energized gas can produce mechanical work. Energized gas can produce mechanical work. Okay? If no energy, no work. So I will take this now. So this makes everything very simple, okay? Now, I'm thinking the same way as you are thinking. Your thinking approach may be better than my thinking approach because you are exposed to technologies, okay? You are exploring technologies. So energized gas can produce mechanical work. Energized gas. So we have to, how to make gas energized? How to make gas energized? Yes. How to make gas energized? How to make gas energized? Okay. Before that, I'm going for comparison of two applications. Air compression and a bicycle engine. Okay. Air compression and bicycle engine. Actually, last time we have learned about the air compressions and systems, if I'm not mistaken. So you have learned something about air compressors. Even engines, you have learned something. Okay. That is for the open systems. So let me look for a picture now. Air compression. Yeah, I'm not promoting brands, okay, but I have to use the picture. Put any question or anything, just let me know. Eh? So here what you are using is this compressed air. Of course, there is a power. Okay, there is a power. You can drive some pneumatic tools, machines, okay, using compressed air. Okay. Okay, you can use as a pneumatic tool. Even you can have very heavy applications. Like this. See. So light applications, of course, even both consider light application because manual consider light. Okay, not heavy. So air compression applications. Okay, here you can see air flow here. See, here also you can see air flow into the machine. Okay, so you have a machine, flow in and flow out. Compressed air in, compressed air in. See, compressed air in. Okay, very interesting. And then again, so after that, put again. Okay, Vita. And after this expansion, okay, after this air leaves. I just put here air leaves. So initially compressed air get expanded. Okay, air expanded. So that is the point. So here compressed air in, expanded means decompressed air out. Okay, so I will put it here. Compressed air in. Air means pressurized air. Pressurized air. Okay, pressurized air. Compressed means pressurized air. Okay, pressurized air. Then once open, or once there is a chance for pressurized air to get release the pressure, definitely this air flow in bulk way. Okay, and then the pressurized air in and depressurized. Okay, depressurized. Depressurized or decompressed. Okay, decompressed. Air out. Okay, depressurized. Another one. okay, lowered pressure. So when the high pressure to low pressure, okay, when high pressure turns to low pressure, actually what happens is this air expands, okay, this air expands, this air expands. This air expands. That is what is happening. Okay. This air expands. And leave this. Yes. So this is what is happening. Okay. So here you can see air in, this understanding is very important, and air out. Okay. So you can see expansion. Okay, air in, expand, see volume increasing. Okay, and finally air is out. Okay, depressurize. So for this expansion, there is a mechanical component related. So this is the drill. See, this is the drill. It's very interesting. So this is the drill. This is the drill. This is the drill. So that is a shaft. You can see maybe a motor or whatever. Not a motor here. It's a. There are some impeller or propeller type of whatever, no motor, because this is a pneumatic tool, and this deliver a work. This deliver a work. Okay, this delivers a work. So this is compression. Okay, air compressor using the compressed air. So this is a pneumatic tool. Work is done, work out. So here, there is an airflow in bulk. Bulk airflow. Bulk in big quantities. Airflow. Okay. Bulk airflow. So pressurized bulk airflow, okay, passing through the mechanical device. There is a work done. Okay, there is a work done. Compressed air. Here. Expanded air. Here. Work out. You see, so nice. The modeling part. Work out. The drill maybe, drill bit. So this is a pneumatic tool, so you can see. So this is not to say energized, but of course it has an energy because this is pumped and compressed, and of course these are considered gas molecules, okay, and they are trying to repulse each other because compressed means they are trying to move apart. So there is a kind of potential, okay, kind of a potential pressure, okay, a kind of potential energy there. So once there is a chance, of course, there is a huge mass flow in a small, through a small passage, once expanded, yeah, it releases a lot of energy, okay. So compressed air has some packed energy because of that compression, but flow is in bulk. So you can study this, okay, Buddha? So here, the energy, the pressure in the pressure form, okay, it's a kind of potential converts to kinetic, okay. Yeah, it is very good. Yeah. Okay. Yeah. So flow energy is there. So somehow converts to kinetic, and part of that, okay, converts to work. So it's a transfer through this equipment. So this is quite interesting. So let's say bicycle engine afterward. I'm taking a bicycle engine now. Okay, I'm taking a bicycle engine. Yeah, this is not about the gas power, but let's say the power of the bicycle engine, how this produces. So initially, within this engine generates sufficient quantity of pressurized, combusted or energized gas, okay? Sufficient quantity of energized gas first generate this. Passing through a mechanical device, we call it engine piston cylinder, makes the combusted gas or the energized gas expands. Same way. High pressure to low pressure, this moves, expands, resulted mechanical. Okay, this is how this is done. So there are two things. Working fluid expansion, and the other is the equipment to support the function. Okay, two things, working fluid and the equipment. Here you can see working fluid and the equipment is the drill or the pneumatic tool. So tool is designed and constructed so that this pressurized air, while passing through this, expand through a rotating component. And this rotating component, of course, receives or delivers some work, mechanical, and then decompressed or depressurized or expanded air moves out. Okay, so this is expanded also. Let me try to this a bit. Decompressed, yeah, or we call expanded air. So you can say expansion produces work. For expansion, you need higher pressure. Okay, working fluid at higher pressure, passing through a component or a device, mechanical device, release or transfer into mechanical work a portion, and the balance exits the device as after expansion. Means not the full 100% available energy is converted, but part of that, of course, significant part of that is used for the work done, and the balance, because this can be further expanded, further expanding, of course, the tool becomes very bulky and difficult to handle maybe, so expansion has limitations. So still a bit pressurized air may be finally leaving to the environment. Okay, yeah, but anyway, this is the situation. So you can see, okay, bulk airflow passing through this, pressurized, expand, and then leave the tool, and the expansion produces work. That's it. So here it's also the same. Expansion, here the piston cylinder, okay, the power stroke is the expansion. Okay, power stroke is the expansion. Okay, power stroke. So we are talking about the power stroke. So combusted gas. Combusted means, of course, here the bitter is, because of the combustion, this gas becomes energized. So I put the word energized here. Energized. Okay. Of course, this energy is received by combustion. You know better than me. Okay. Energized gas expands. Yeah. Expands. Yeah. Resulted mechanical work. Because when that gas energized, means faster molecular motions. naturally it becomes pressurized. So pressure becomes high, temperature becomes high, because temperature also, it's a reflection of the kinetic energy of the gas. So of course combustion, add heat. Heat means adds energy. Energy means this molecular motion becomes very violent. So their space is limited. So they are very violent, so that in a limited space, this violent nature of molecules creates a pressure. Okay, creates a pressure. Actually, pressure is none other than this violence of these molecules within a limited space. So they are trying to escape, but no chance. But once, okay, the piston has a possibility to move, so this air pushes the piston, which means this gas or the energized gas or air expands. And the piston moves because of this power of this gas. Power of this gas means gas power. Okay, gas power. So gas power produces mechanical work. Okay, so you no need to remember this, but to have a good sense of understanding makes naturally you remember this. So two things. So quite interesting. Okay, so anyway, both compression and bicycle engine produce work. Okay, compression through this pneumatic tool produce work. It's a big work. Yeah. See, even you sometimes you can drill the holes in metals, but if you do this manual, it is tough. Okay, I hope you can understand this. It's an enormous work. Same bicycle, yeah, riding at high speeds, yeah. It's because of this gas power. So you know what gas means now. No need to memorize, but whenever you need to have good thoughts, series of thoughts, when you develop the things, your understanding about gases will appear. Okay, so try to have some good sense of understanding. Yeah. Technology is something you are seeing. Okay, you are seeing. You are seeing in the mind. Okay, of course with the senses, but finally this technology. Example, seeing the space. I have explained to you, maybe seeing the space. Avakashya කියන එක ඇහැට පේන්නේ. Space you have to see through the mind. Same way technology you should see through the mind. Now that is very important. Okay, seeing through the mind. Now, another word for that may be understanding. Okay, another word may be understanding. Good. So the gas power with these two examples, air compression, bicycle engine, I think would be all right. But our cases, yeah, bicycle engine and air compressor, yeah, this pneumatic tool, expansion is the common phenomena taken place to deliver work or gas power. Okay, so the lessons, two lessons. Yeah, two key lessons. To produce mechanical power from gaseous working fluid. A bit more technical. Okay, gaseous working fluid. Because in the air compressor, this driving this pneumatic tool, yes, air works. That's a working fluid. In your bicycle engine, the combusted or energized, yeah, this gas, okay, that is pressurized also because it is energized in a limited space. Yeah, that is the working fluid, expands. That is one thing. And there is other thing. There is equipment. You need an equipment through which the gas expands and produce a useful work. Okay? To produce a useful work. So, equipment, expansion. So you need both. Okay? So, expansion. This is important. And equipment you need. So, pneumatic tools, what happens? This case, let me take a snapshot. Equipment, expansion. Okay? Equipment, expansion, equipment. So, expansion of working fluid, not the expansion of equipment. Okay? Equipment. Okay? Through which the gas or working fluid expands and produces work. Okay? Or simply I say equipment to facilitate the working fluid to deliver a mechanical work. Okay? In other words, that's equipment through which the gas expands and produce useful mechanical work. Okay, I believe you can understand. It is a little bit, quite philosophical also. You are learning, not like mechanics. The mechanics and all, they know how to repair, and they are the mechanics. In the garage. So their focus is only on the equipment. Okay, so they do this replacement of parts and all, maybe cleaning, servicing, whatever, change oil. So their focus is on the equipment, not on the working fluid or expansion. Fine. So they have the equipment repair knowledge. Okay, but when you design, develop, and of course when you innovate, so you have to have both this combined view. You are facilitating the working fluid to produce work. So your development equipment is for the working fluid. So priority is given for the proper evolution of the thermodynamic states of working fluid. For that, you are catering or you are supporting with the equipment design. Understand? That's all. So if you are changing the working fluid, example, petrol to diesel, you have to review your equipment from petrol-related engine to diesel-related engine. Two things. Okay? And also the way you are energizing it. Maybe, sometimes maybe ordinary standard engines, or maybe sometimes even for the petrol, now there are fuel injections. So fuel injections and the normal carburetor systems, two different systems. Maybe you have to facilitate the equipment in little different ways. Okay, there can be little different ways. So I hope you can understand the philosophical aspect of techno-philosophical. Okay, even technology has philosophy. So let's see techno-philosophical aspects. Actually, that is what you are learning. Okay, technology and the techno-philosophy. That is very, very important. And if you can catch the techno-philosophy, I would say you are creative, and that is what you have to. Okay. Technology. Yeah, it's very technical. Techno-philosophy. Yes. Two things. Okay. I would say two things. Techno-philosophy provides innovative and appropriate technological solutions. Okay, so they are technocrats. Technocrats. It's very important to have a techno philosophy. Okay? Yes. Secondary is the technology. Even techno philosophy creates technologies. Okay? Creates technologies as well. If it's only the technology, you don't feel that tasteful, not that tasteful, because lack of creativity. Maybe too routine, too routine. Example, let's say in the CEB, let's say electricity board. So if they do the same routine works, maybe power generation, transmission, distribution, and power supply maintenance. If they do the routine works in CEB, they are not that philosophical. Of course, they are energy. Yeah, they have to improve the things, true, but if they are not that technocrats, okay, if they are not that techno-philosophical, they cannot be very good solution providers. They can be, they cannot be innovative enough. Okay, so you have to go with philosophies, even when it comes to technologies. Okay, Bhutana, that's why even I'm explaining these things for you to understand this. So understanding technology is something that you should pursue. Understanding has no limit. Okay, so you should understand better than us because you are the future generation. So with these lessons, okay, with these lessons, you will be moving in the right directions. So techno philosophy has no maths, but there are a lot of ideas, creativities, imaginations, innovations, plenty. Okay, that's why Steve Jobs said, "Stay foolish, stay hungry." That is for these technocrats, innovators, these technocracy people. Okay, those are for the philosophers, techno-philosophers. Steve Jobs is really great. But just to learn technology, that is not enough. Yeah, that is not enough. So remember the word, okay? Be techno-philosophical. Because even I can see some students are asking questions in the class. So they are quite thoughtful, very thoughtful. They are trying to imagine, understand the things. That is wonderful, really. That's what. Seeing the unseens, okay? Seeing the unseens. You should be seeing the unseen. Unseen. You should be that philosophical. Even a designing of a piston cylinder. It is very wonderful. You have to think about your working fluid, how you can guide this expansion, and how this design can be the space within. Cylinder is a space within, and piston is another component to this evolution of the space during the power strokes or whatever. So your thinking is different. So your technology, you are talking about energy, working fluid, space, properties and all. It is not about so solid cylinders and piston. Those will appear, of course, at the secondary level. You understand? Very good. Okay, at the secondary levels. So this is about gas power cycles. So see, so now is 10 plus. So still we moved very solid way, but when you are approaching with a very good thoughtful approach, if you have, yeah, it seems a bit slow, but that is very solid and one-time learning, Putta. Okay, good. So you know now two things we need to understand gas power. One is the expansion and other is the equipment to facilitate this expansion. So you are talking about this too. Okay, you're talking about this too. Same way for refrigeration cycles. Yes, you have this changes, compressions, and others. There may be some working fluid changes. So the working fluid and the equipment to support this working fluid transitions in the cycle. So in power generation, I would say it's expansion that produces power, the power stroke or delivering of power. Okay, so when it comes to cycle, there can be other components as well. But for this power stroke, this is the one, expansion. So let me move forward, Putala. So we have gone through this. Delivering of mechanical work by using energized gas. So high thermal energy, compressed or pressurized. And then gas expansion takes place. Okay. And when it comes to cycle, can be same or similar quantities of substances performing in a thermodynamic cycle while producing a mechanical work. In short, cycle means this repetition of the cyclic repetition of thermodynamic states of same or similar quantities of substances. Okay, same or similar. In the motorbike, it's not the same but similar quantities of substances. In gas power. Okay, so same quantities can be in the Stirling engine. So external combustion, Stirling is another gas power. So they are the same quantities, not to say similar. But internal combustion, it is not the same but similar quantities. You should understand this. Okay, so later we will understand this when we connect this power cycle with the real applications with the components. Yeah, don't worry. So now we have a basic understanding about gas. Basic understanding about gas power. And basic understanding about the requirement of this energized gas and the gas expansion. Of course, only energized gas expands. And then the equipment needed for this. Okay, it's the same thing. So same or similar quantities of substance. And this gas, or maybe the gas, performing in a thermodynamic cycle while producing mechanical work. So gas is the working fluid. Okay, same thing. So here, this is gas power application. This is not in a cycle, maybe. A quantity of gas producing a mechanical work, rocket propulsion, let's say in a rocket. අහස් කූරක් කියලා හිතන්න. වෙඩි බෙහෙත් කිව්වර ඉච්චාම ඒකෙන් වෙඩි බෙහෙත් පිච්චිලා one somehow the combustion of that වෙඩි බෙහෙත්, I don't know what's the English name for that. Once the combustion finish, because the finishing of the veди behead, so after that no forming of gas power, it's gone, same like rocket propulsion. So there should be working fluid. It's not operating in a cycle, but of course for the space applications you have to carry enough fuel. Okay, so this one is propulsion, that is following the Newton's third law. Every action has a reaction. Okay, yeah, so propulsions. So there it's taken place, rocket propulsion, even in the engines, also in the plane engines, this propeller engines. Also you can see that kind of propulsion. Propulsion, we call it propeller. You push the gases and in return you are moving forward. Yeah. So the plane push this pressurized, energized, released to the atmosphere. In return this moves forward, especially the jet aircrafts and all. So all mechanical applications. Give me a second, Pita. Yeah, Pita. So power. Yeah, I put this as generating process. So fuel, combustion. So when something combusted, some release energy, heat, we call exothermal. So the fuel, petrol, diesel, even firewood, when burn, means react with oxygen, it release energy, we call exothermal. So this fuel are exothermal, reacting chemical compounds. Once combusted or reacts with oxygen, generates higher quantity of pressurized, combusted, energized gas. Actually energized, that's the word here. Yeah, generates higher quantities. That's how we have to make it. Okay, because it's taken place in limited space, then passing through the nozzles. Okay, make the combusted gas, pressurized gas, energized gas, expands, propels the spacecraft forward. So nozzles are the equipment here. There can be, of course, the combustion chambers. After that, these nozzles to exit this energized, pressurized, combusted gas, so that it expands and ejected. So as a result, this craft moves forward. Okay. So rocket propulsion may be not operating in a cycle, but we have to carry enough fuel. Yeah. Yeah, you can accept this at the moment, but when it comes to the air compressors, sorry, not the air compressors, the turbine engines or the turbines, still there are thermodynamic cycles, okay, when it comes to the turbines. But here for rocket propulsion, this can be a fact. Okay. So Gas power cycle, power generating strategy, same as mentioned above. So generate sufficient quantity of pressurized combustion gas. Pressurized means it is one way you are mentioning energized. That is for gases. Somehow energized. Yeah. Somehow energized. Because relatively you are keeping all in a limited space, confined to limited space. So about to move at any given chance. That's why passing through mechanical devices makes the gas expand, resulted mechanical work. You know this now. Power generating strategy, know this, you know this very well. Yeah. Energized gas, pressurized as well. Then through the mechanical device makes the combusted gas expands. Okay, after expands. That's the piston cylinder. Okay, this is about the power stroke. Resulted mechanical work. So you need two things. Cycle, thermodynamic cycle can be there, or the working fluid should be there, and there should be an equipment to support to function the cycle. Okay, so in this cycle, working fluid remains, if working fluid remains as gas all the while, we call it gas power cycle. Okay, example, petrol engine. Not the same but similar substance operating in a thermodynamic cycle. Okay, so petrol engines, diesel engine, biofuel engine, heavy fuel cell driven engine. So what are these? Petrol engine. Petrol is the means of energizing the working fluid, combustion of petrol. Engine is the equipment. Diesel is the means of energizing the gas or creating the energized gas, combustion of diesel fuel. Engine is the equipment. Biofuel, fuel related to this. Working fluid again, engine is the equipment. Heavy fuel is the working fluid related, engine is the equipment. So fuel cells. Fuel cells are of course the fuel should be hydrogen. So anyway, engine is the equipment. Jet engine. Actually, jet engine here, the jet engine is the equipment. So here the combustion, yeah. So jet is the way the working fluid exits. Somehow jet related to the working fluid. Engine is the equipment. Aircraft turbines. Turbines, you are seeing the mechanical part only. But of course, through this, energized gas expands. Okay, that's why. So you have to have this working fluid, and also you can see a cycle, and of course the equipment, even the engine. You know there are 4-stroke and 2-stroke, whatever. You can see the cycles. So energy expansion, power. Yeah. The working fluid expansion is the power stroke. Then you may have the exhaust. Then you have the suction stroke. And then you have the compression stroke. So those are the arrangements. For these arrangements, this equipment is important. So out of 4 strokes that produce or provide a cycle, only one stroke, that's the power stroke, only produces the power. Okay, so the cycle has many, or the 4 stages, not to say 4 stages, the 4 thermodynamic processes. Okay, or 2 stroke, maybe there may be 2, significantly 2. Yeah. So somehow you can see this working fluid, the equipment, and this changing of thermodynamic states in cyclic form. So that's how the gas power cycle we have to look into. So working fluid get energized and ready for expansion through a mechanical device. Okay, so that is what the basis of gas power. Working fluid get energized, thermally energized, of course, and ready for expansion through a mechanical device. Thermally energized, there can be spark or whatever combustion, and this working fluid receives energy and produce work when expands. Of course, not 100% thermal energy produce work. There can be a loss. So this can be a petrol engine, diesel engine, biofuel, or whatever I mentioned in the previous. So working fluid remains as gas for gas power cycles. So that is the specialty of separately treating gas power cycles instead of talking commonly about power cycles. That's okay, but you can see no much deals when it comes to the techno-philosophies. You have to take the philosophy as well while exploring the technology. That is very important. So, of course, you know that equipments are there to facilitate this expansion, and it is not possible to transfer all the thermal energy into mechanical work. It's a practical fact. Okay, and we call this is mentioned, or this is highlighted as a statement by the scientist Kelvin and Planck, maybe Kelvin Planck statement. We call this, which means it's not possible to transfer all the thermal energy into mechanical. This is part of second law. Okay, this is part of second. One is the Clausius, that is about the entropy change, and this is a statement. Okay, you have to understand this. No need to remember this, but you can understand this. Of course, you have to remember the name in connection with this understanding. Okay, because you may have the understanding if you forget the name. And in the exam, if asked what's Kelvin Planck's statement, even though you have the understanding of this phenomena, you cannot answer if you forget this. So I think now you can remember this Kelvin Planck statement. Same thing. Thermal process in a cycle receives thermal energy somehow, maybe from combustion. Useful work is done. This is the W net, and there is a loss, balance. Balance means energy balance. Q useful is Q in minus Q loss. That's a balance. Okay. That's the balance. Same line. If you take 200 rupees to a shop, you spend 100 rupees for a phone card, you get a balance of course, 200. No, let's say 500 not. If you bring 500, you buy 100 rupee phone card, balance you will get 400. So 5 minus 1, 500 minus 100 is 400. Or else 400 plus 100 is 500. Or 500 minus 400 is 100. You can express this balance in any of that three ways. So I bring this Q useful here, so Q in minus Q plus. Okay. Generally, Q useful is, if it is measurable, of course, can be measured. There are ways to measure Q useful. So Q in minus Q useful is Q loss. So the efficiency is useful divided by the energy in. Q means energy. So Q useful means the, of course, that is work done. So energy transfer to work during expansion. W net by Q in. Okay. So in the most appropriate, this is the Kelvin-Planck statement. In the most appropriate expression of the efficiency, you can have this one. I think that is for sure you can understand. So not possible to have 100% efficient. In short, efficiency. Neatize the efficiency. Okay, Putana, I hope you can understand this very well. It's the same thing. Yes. This is what we have done now. So this is this picture is a model of a heat engine, let's say. Heat engine means that engine, we use this term when we derive or produce mechanical work, we call it engine. So here we use thermal energy or heat. So heat engine means engine produces mechanical work by using thermal energy. Okay. So here expansion of working fluid if steam. Yeah, this is very nice phenomena. So if steam once expands means releasing energy, and finally it cannot maintain that energy levels anymore to be in gas forms. So molecules become together and turn into liquid. Okay. No more ability for expansion, but still there is a thermal energy at large. In the vapor turned saturated liquid. This is my own text. Okay. So that is expansion of, if steam means expand and finally it can be totally liquid, but gas means releasing its energy content and become molecularly more silent but still remain as gas. Molecularly silent means low temperature, low pressure, and bigger volume can be. Okay, molecularly silent. Okay. And molecularly silent expansion of gas. Still in the gas form, but there is a significant portion, but cannot be delivered a mechanical work. Those are some limitations. That's why it is not possible to transfer all the thermal energy into mechanical. Same if it's steam engine. Once turned liquid, maybe high temperature liquid. So liquid cannot be expanded anymore, once turned liquid. Only gas can be expanded. Okay, gas can be expanded means release energy and turns into liquid, and that's it. Certain thermal energy is there, that's why it is not possible to convert 100% the thermal energy into mechanical. So that is 100% means all the thermal energy. This is also, I just put this word. So I hope you can understand this. So this is a thermal process in a cycle. It's a processes, receiving energy, work is done, and the balance, of course, it's a loss. So for cycle, thermodynamic cycle, so the sequence of state evolutions, thermodynamic state changes. Yes, the working fluid is undergoing that, so working fluid remains as gas for cycles. And definitely you need an equipment to support this function. Can be engine, can be a turbine. Both performs expansions. This is, of course, technology. This is, of course, technology. Okay? This is, of course, technology. So there can be gas turbines, and there can be engines of different configurations. Even for turbine, gas turbine, we can mention as turbine engines. Still okay. So others can also be engines. Now the turbines can be special engine types. Turbine engine we can call. Engine is a general word. So different configurations for different working fluids. So you can have for diesel power cycles. For gasoline engines, you can have gasoline power cycles. So for gas turbines, you can have gas power cycles. Because there can be different strategies of energizing using diesel, using gasoline, different strategies for energizing the working fluid. Yeah. And also there can be internally energizing, internal combustion. Okay, so within the fluid, somehow energy is created. Diesel and petrol engines, within the working fluid, somehow this energy is added just by sparking some fuel and igniting. Or because of the working fluid pressure, maybe you inject some fuel and ignite. So spark or compression ignitions, or there can be combinations. or even there can be external energizing by combustion, maybe same. That is something like Stirling engines. Yeah, later we can learn about the Stirling engines as well. So there can be internal combustion and there can be external combustion. Internal combustion engines we call IC engines. Okay, IC engines. So external combustion generally you can call as EC, but we are not using any terminology like IC. IC engines is internal combustion. Mostly popular, compact. Okay, there are some user friendliness of IC engines are more. Okay, but external combustion and anyway externally energized engines, there can be even with the solar thermal application we are using Stirling engines, Stirling cycle engines. Even with thermal combustion sources we can use Stirling engines. So then it can be external combustion. Somehow I believe this slide is quite clear to you. Okay. And of course we can minimize this energy loss if you can recycle. If you can recycle. So for the thermal process, same energy in maybe, but the same energy in for the process, but the fuel or energy you are adding is reduced because you are saving here, recycling. So same useful energy, same in for the thermal process, but because of the recycling, your this addition of the energy input externally you are putting here maybe in terms of fuel or some external combustion, this can be reduced. Okay, so this kind of solutions. So here you have the combustion process, power generation, and recycling. So two technologies. Okay, one is for this engine technology, the other is the energy recycling. Together means two technologies combined for ultimate solution of energy savings. We call this kind of things as hybrid solutions. This is not a proper one, of course. This is just a mentioning of this hybrid solutions. Maybe this may be more proper. One way this loss part is recycling. So for the useful, some part is you are recycling, then your engine output can be lesser than the useful, because engine out is useful minus recycle minus electric whatever, even if you can add electric charge. See? Recycling, electric, so your usefulness the same, but the engine out is little now. So definitely you have a smaller energy input. So you can have a smaller engine, no, less energy consuming engine. So you can have the full mode or even the battery mode, recycling, or even electric charge. Yeah, you can charge this somehow. Anyway, hybrid technologies, you have to explore this. Maybe while driving, you can have solar energy. So hybrid solutions. So in future, hybrid solutions can be different from the current solutions. Similar concepts, but different solutions. Yeah. Pre-electric charge vehicles we can see now, but there can be on-the-road electric charging as well. Recycling, of course, taken place when you are running down the slopes or braking. So recycling takes place. So on the road, electric charge is also possible. So off-road also possible electric charge. So somehow combined solutions. So we call hybrid. So you have this, the energy input to the engine can be minimized. Yeah. Still you have to have good engines. Because if no recycling, if no electric, still you can run this if the engine is big enough. But of course, then you have to consume more energy for this useful. So there can be controls, lot of solution approaches, even you can try. Now see this engine technology is pretty much established. New technologies, recycling, storing energy in batteries. Battery technology means electrochemistry. Yeah, new technologies, electrochemistry. So not necessary to be electrochemist, but you can explore developing batteries for this kind of applications, automotive applications. Okay, electric recharge again can be related to battery applications. Batteries, the battery energy storage applications. Yeah. So lithium, iron, or whatever. Yeah, you can see the battery technologies you can explore. That's why now the automobile technology, of course, other than the dynamics and the mechanical and this thermodynamics, now new dimensions are appearing. I don't know why these solutions came so late, even though this looks straightforward. Yeah, so the electrochemistry is the latest addition of technologies for this hybrid power solutions. Quite interesting, Bhutala. Yeah, you can explore this. I just put this on it. So this is nothing to do with gas power cycles, but when it comes to the application trends, so this kind of the energy balances, energy solutions, automotive energy solutions, we should be aware enough. Of course, my knowledge on this is very little, even though I put this. Knowledge on this is very little, but everywhere you can see this energy balance in useful loss, recoveries, reduce. So reduce energy, reuse energy, recycle. So reducing, reusing, recycling. Those are the green concepts in engineering. So energy reduce, energy reuse, energy recycle, greener concepts, environmental friendly concepts. Even in process, material reduce, material reuse, material recycle. So those are the greener technologies. So we are going towards greener technologies. So again, the techno-philosophies. These are techno-philosophies or strategies makes the solutions better for the societies. So here you can see hybrid technology because many approaches combine here for single purpose. So engine technology, batteries, solar, water. So those are hybrid solutions are like this. The hybrid, the word hybrid is not for vehicles. Hybrid means a combination of technologies for a single purpose here for the vehicle issues. Okay, for vehicle concerns, for single purpose energy saving solutions. So different technologies combined. It is not only automotive. So hybrid solutions. So your vehicles can be hybrid. In future, motorbikes can be hybrid. Even refrigerators can be hybrid. Even power plants, of course, they are combined cycle and all, there can be hybrid solutions. So what hybrid means, you should know the meaning of hybrid. Also for your projects, you can think of hybrid solutions for as innovations for your projects or whatever. Even thermal related, thermodynamic related, heat transfer related. Looking into hybrid solutions is very, very innovative, cost effective, and it's a must really. So that is about power cycle, gas power cycle, concept behind concepts. And let me add a new slide here, Buddha. How to energize working fluid. How to energize working fluid. You have to understand the technologies, because the strategy is you may have the working fluid. You may have the working fluid. So, if unenergized, okay, no work output, okay, no work output, W net is 0. So, no work output. Okay, W net is 0. If working fluid is not energized. If working fluid is not energized. So that's the point, okay? If the working fluid is not energized, means if there is no mean to energize working fluid, if there is no mean, or if there is no mean or method or strategy to energize, if there is no mean to energize, means no engine technology is nothing. If working fluid is not energized, means your engine or the equipment can be malfunction. Or if no means, also W net is 0, means no engine or nothing. Okay, so it is very important to bring this energy. How to energize? Okay, how to energize? So this one we will consider now. How to energize? We will start from a known point. We will start from a known point. This one. You internally energize this. Yes. Okay. So you can internally energize this. So how to energize? So the strategy you have to understand. The strategy. Strategy. Okay. Working fluid. Strategy. Yeah. The strategy. Okay. So you should learn, or we should understand, working fluid. Okay, let me go for a new slide. Okay, anyway, let me go for a new slide. So this one can be before energizing. Before energizing. Okay, working fluid before energizing. Or let's say, instead of before energizing, let's say unenergized. Unenergized. Okay. and I'm take the same working fluid, energized, energized. Okay, energized. So after that, we are building the concepts. And don't worry, you have W net. You deliver this. Okay, you deliver this. So after delivering, so here you are. Okay, I think this one, I'll leave it here if I need to take it back. W net. Housekeeping issues here. So after energizing, you deliver the work. This labels now. First one is not energized, or before energized, energized, de-energized, or energy is released after energy releasing. Okay, before energized. energized and delivering. Okay, energized and this may deliver some. This is not relevant. Before energized, 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 de-energized. Okay, de-energized. Yes, before energized. You have certain pressure and a volume. Okay, and your energy level. E1. For this case, before energized. Okay, and then energized. P1. This is quite time. V1 can be the same. Okay, P2. V1 can be the same, but now the energy level E2. Let's say I at the moment I put E2. E2. Let's say P. Yeah? P. V. P2. V2. V2. Okay. Expanding. So you know that V2 is much bigger than V1. We call this expansion. Okay, expansion. Okay, and one more here, not only V2, here comes the P1, sorry, P2 and P1. P1, how to say? We can say something, okay? P is very much larger than P1, okay? Also, P is very much larger than P2. And P2 can be practically, P2 can be not that, but of course larger than or equal to P1, but let's say P2 is can be larger than P1. Can be. Okay. So this is after expansion. Okay. So same way here, energizing. I can put this one, P2 larger, P larger than P2. That's a sudden. Or P larger than P2 is pretty much obvious. Okay. You are going to learn something special here. P larger than P2 is pretty much obvious. And I take this out. P larger than P2 is pretty much obvious. And working fluid, okay? Before energized, I put it I have to put it like this. Not to say before. Just before energized. Just before energized. Just before. So, working fluid. The other one is just energized. Okay, just energized. working fluid. This is okay, de-energized. Just de-energized. Okay. De-energized. Okay. Because we are talking about the strategy. Just before energized. Okay. So can be this. Okay. Just before de-energized, sorry, just energized. Can be this. Okay. Yeah. So if this direction, arrow direction, you have to have an arrow direction here. So let me take this out. Ignore the arrow direction here. So just before energized, just energized. So pressure for sure goes high in some cases. Okay. And some cases pressure can be very close to P1. Pressure is very high, can be very, very close to P1. So this is compression makes the, yeah, I just put here, later I will explain, I put compression, ignition. Okay, energizing place. So case 1, P can be P1. Okay, P can be P1 during the energizing. Okay, there can be other situations. So P can be P1 during the energizing. Even in a millisecond, V can be changed. V can be more than V1. Possible. Okay? Now let's say this is possible. Because energizing, if you want to remain P as P1, definitely your V1 will go high. Second situation can be your V can be V2. So V can be V2, then your pressure will go high. Okay, so here volume will go high. So this is compression ignition, or we call this is the technology, we call this constant pressure heat addition, or constant pressure energizing at constant pressure. at constant pressure. Energizing means heat addition. Okay, constant pressure or heat addition, constant pressure. Okay. So V equals V2, pressure goes high. So this is generally for the spark ignition, maybe. I don't know, but possible. Compression ignition, maybe. Yeah, but surely this is energizing at constant volume. Energizing at constant volume. So constant volume heat addition. Okay, this is the strategy. So both cases P is very much greater than P2 because expansion. Okay, both cases. So I will bring that down because of expansion. Energized and expansion, P is and V2 is very much greater than V1. I put this separate for all the cases because of expansion. Too small, too big. Just one. Energizing at constant pressure. Energizing at constant volume. Possible. That is related to the equipment. Okay? That is constant volume heat addition. Because of expansion, you have a shooting up of pressure. Yeah, compared to P2, this is quite high. And also because of the expansion to take place. V2 is quite larger than V1. Okay, so I combine energizing and expansion. Okay, so there can be constant pressure, energizing at constant pressure. Not to say V equals V2, this is V equals V1. I made a mistake. Okay, so V equals V1. So the working fluid just before energized, volume same as working fluid just at energizing, then constant pressure, constant volume, energizing, co-heat addition. When P is P1, so energizing at constant pressure or constant pressure heat addition. So in this case, V is changing during this process. So V changing V is in this direction. Changing V is greater than V1. Here changing P is of course it is more than P1. That is how it is. I hope you can understand this. Behind this there are technologies. Okay, but here in this crafting of technologies, there are constant volume unchanged, and energized. Your pressure will go up. Pressure unchanged and energized. Your volume will go high. Okay. So generally, these engines, okay, so or these equipments we are using for energizing the working fluid, energizing working fluid. So two different strategies: constant pressure, at constant pressure working fluid energized, P is P1. So at constant volume V equals V1, also working fluid energized. So two different equipment designs. Okay, two different equipment designs. Two different equipment designs. Okay, so and this approach may be for different working fluids. So working fluid and the equipment go hand to hand. The reason is the nature of working fluid connected with the nature of equipment design. So the reason. Nature of working fluid and the equipment. Okay. And there can be other approaches. I would say 3. No one can say not possible. 3 can be something like this. First, maybe you can follow 2 plus. Next can be 1. Because constant volume heat addition after that, of course, pressure will go high. Then you can go for constant pressure heat additions. So there can be a situation like 3 as well. This is the situation 2. V equals V. So situation 3 can be a combination of strategy 2 and strategy 1. Strategy. Strategies 1, 2, and 3. And now with the technologies, even there can be more complicated because now there are programmable and much controllable way of energy additions, so that now there can have, even though these 3 are the major, there can have quite, how to say, many combinations. Okay, there can be quite many combinations. 1, 2, 3, and of course because of expansion. So behind these concepts, the philosophies or the concepts itself. Okay. I hope you can understand, Bhutala. Okay, good. So you have this 3 situations. And 20 plus now reduced to 17. Why? You have issues. Now, PV diagram in energizing strategies, PV diagrams. P is the pressure, V is the volume. Now we have energizing strategies. We have what? We have learned 1, 2 and 3. Okay, 1, 2 and 3 we have learned as 1, 2 and 3. This one. Okay, this one. Let's see, we will draw one by one. We'll draw one by one. Okay, slowly building up your knowledge step by step. Okay, so PV diagram. V, volume. Actually, the more proper word for this is the space. Okay, space is the more proper word. The space occupied by this working fluid. What during the just before expansion, just after, sorry, at the expansion and just after expansion. So let me keep your memory here connected with this. No choice. Put this into side, should be enough. Okay, yeah. So first case, constant pressure heat addition. When there's a constant pressure heat addition, of course, P1 V1 just heat addition, energizing. So this is the big one. So your working fluid just before you have the values. Make this line bit thicker. Give me a second, Pita. Okay, Pita. I have this initial. Okay, P1. This is your P1. This is your P2 point. P1 to P2. I think I changed this and style to a dot T. Okay, P1 to P2. Okay, good. P1 to P2. Now to say P2, that is P. Okay, P1 is P. This is your V1. Naturally, V will be bigger. So constant pressure heat addition. Okay, interesting. One. This is one. One. Okay, so only this heat addition part. So here you should know that. Just before and just energized. Just before. Just energized. A little bit big volume. Okay. Same pressure. Interesting. Okay. Feel that. I will dim this. Lowering this a bit. PVA is here. P1, V1, E1. No place to put. I take it out. P1, V1, V1. Of course, E is much more larger than E1. Okay, that is no need to say, but anyway. That is obvious for all. Good. Then I will go there. Then I will go for two strategy. V is V1. Then what happens? V1 is V. So V becomes V1. V is V1. Then this is your P2. Because P2 is, sorry, this is your P. P is more bigger than that is P here. P1 is P. This is P is P1 here. I have to put P1 is P1. P is P1. Okay, P is P1. Take this P out for clarity. So this is your P now. So no V here. P is not here. So this is the process 1 to 2. Okay, quite interesting. I put this here. This is This is 2, this is the PV point. Bring the same, because constant volume, so this point. I think that is okay, good. Nice. Energy addition. Put 1 star here as well. No harm. I'll put 1 star here. The fire brings the energy there. This 2, constant volume. So no change of volume. When heat added, your pressure will rise. Constant volume. Constant pressure heat added, your volume will rise. Then I will go for the item 3. That is not 2. You can refer right side. This is 2. Item 3 is this. This is item 3 now. Yeah, item 1. This is that strategy. Item 2. This is the strategy. This is item 2. This is item 3. This is the strategy. First, 3 is 2 plus 1. 2, and then I will add 1. See what happens. Yes. Item 3. Everything. So your volume will be big as well. Let me put it here. This is fine. So this is your P and the V value. Initially V equals V1, but finally you have a different V. So finally you have a different. So This is V equals V1 process. Now another P equals P1 process afterward. Finally, you have P and V here. So it starts here, ends here. So now this is combined. Interesting. This is 3. Okay. So this is the energy addition, so energizing strategies. Okay. Energizing strategies. That's all. Here we have done only the energizing, not the cycle. Cycle has several pieces to connect in this PV diagram, but energizing, these are the 3. This is 1, constant pressure heat addition, constant volume heat addition. This is combined. Of course, in a combination, the best possibility is this, because otherwise, if constant pressure follows constant volume, your pressure rising is very high. But volume plus pressure, it is still manageable. Okay. So heat additions. So energizing. It's quite interesting. Quite interesting, isn't it? So this is how produce the gas power. So this working fluid, the amount, the volume is depending on the application. In a ship, if this is yeah, back again put after signal interruptions. Okay, just reduce one more 15 only. So in big diesel marine engines and a small motorbike, the power requirement is different. So even if you are using the same fuel, let's say diesel and anyway, different working fluids, that is fine. Marine big diesels and your motorbike engines, for your motorbike engine needs a very little power compared to the big marine diesel engines in the ships. So here you have a very small volume. Your pressures also may not be that high. A simple designs. Here piston cylinders may be smaller space in the cylinder for piston to move. But in marine engines may be a huge displacements of the pistons, bigger volumes, and many cylinders. So we call it the design for the capacity matching. Okay, design for the requirement. So here in general, in this techno-philosophies, we are getting a little working fluid just as volume V, but in practical, you have to connect this. So bike engine, car engines, lorry engines, train engines, ship engines, power generators, like the diesel generators. There are diesel generators in megawatts in Sri Lanka also. So you can see different volumes of working fluid. Yeah. Okay, different volumes. Also different masses. Okay, are performing this work task. Okay, so this is only the energizing part or energy addition. So three cases, 1, 2, and 3 means 2 followed 1. Okay, 2 plus 1. So 2 followed 1, 2 plus 1. Followed means after 2, you add 1. Here. After 1, if you add 2, maybe it goes for very high pressures, and that is practically there may be difficulties. So these are the 3 types: constant pressure, constant volume, and this is combined heat additions. Okay. Give me a second, Buddha. This is a PV diagram. I just took this. Only focus on 2 to 3. Constant pressure combustion. Can you notice it? Constant pressure combustion. In the PV diagram, see flat 2 to 3. And this is in our PV diagram. See flat one here. constant pressure heat addition. So I put this one. As a picture I can put here. This is not a diagram. We just learn only 2 to 3. Okay. See, flat line. Here it's the same. Okay, so we are learning something very important. Okay. Similar way. Another one. Again observe in PV 2 to 3. Constant volume. We call it combustion, of course. We call it constant volume energizing the working fluid 2 to 3. So let me go to our concept building. You can have a look. See constant volume. See, we put the combustion, energy addition, star. Constant volume combustion. Okay. So here the fuel or the working fluid and the equipment combinedly derive this. Okay. Understand, Bhutana? You can say it. Be patient. In this PV, see 2, 3, and 4. Constant volume, constant pressure. That is, in our case, that is process 3. Let me take a snapshot. This is no use. This is the one. Okay. This part. Okay. This is the most important part we have to recognize. Energizing. So we call this dual cycle. Okay, dual cycle. The diesel cycle, Otto cycle, and dual cycle. Diesel cycle for diesel, Otto for gasoline or petrol, and this one is dual cycles. Maybe for enhanced efficiencies and all. For anyway, the equipment or the engine design is important. So we have done this very basic but important one with some valid reasons. So I'm not introducing you a cycle, but I'm introducing you the ways how the fluid or working fluid and the equipment can combinedly strategize to energize the working fluid to derive some work. So here, so today we have learned a lot from gas power cycles, and energizing, and the three modes of energizing, 1, 2, and 3. You can see all the three are connected to standard cycles. So here, that's a balance, you know. We know only 2 to 3 here. We learn 2 to 3 only. Here we learn 2 to 3 only. Here we learn 2, 3, and 4. The key process we have learned. The balance is quite simple. Okay, I hope you learn this in very simple way. The energy aspects. Okay, very simple way. Gas power cycles understanding. Today is the first lecture. I believe you have done something very good. Okay, so Kelvin-Planck statements and efficiencies, expansions, concept of hybrid. Okay, we have learned all. So quite good. And I think enough for the day. So it's 12:15. Any questions before wrapping up? Putana Terunada. Any questions before wrapping up? Did you understand well? Okay. I believe you understand this very well. Okay. Have some imaginations, good imaginations. Philosophies behind this. Of course, these are related to physical things, technologies, but there are philosophies behind this as well. So hope you can understand, Putala, this. So next week, we will be covering all the 3 cycles in very comprehensive ways. And also we will be covering remind me to cover this turbine engine cycles, because these are turbine engines. It's a different cycle, also related to this. So let me introduce that as well, not now. So we will learn 4 cycles in the coming session, coming Friday. After that, we are ready to do the questions, revisions, and everything. Okay, because you have noticed that the syllabus components, okay. So analyze gas power. Before that, we have to understand the gas power cycles and the applications. Okay. So vapor power cycles, that is ranking cycles. We have learned Carnot cycles, we learned reverse Carnot cycle, we learned TS diagram of refrigeration cycle, we learned Steady flow energy equations we learn. Entropy, Clausius inequality, and Kelvin-Planck statements we have understood very well. Then entropy in thermal systems. We have learned a bit. We have to drill more. Actually, it's enough if you can go through. It is good because textbooks are given, notes are given to you. So second law, we have understand very well beyond the definitions. Energy balance, applications, we have done a bit. Exercise, but we have understood it thoroughly. We have understand it thoroughly. And the first law of thermodynamics, that is energy balance. We came to know this. And we have moved with different examples of many, like balloon examples, earth moving cycles, and many such. And even today approach is something like a story type to learn thermodynamics. But that's all. So any questions before winding up? Any questions before winding up? So hopefully next month, March, yeah, still we have 6 weeks. We can do this very nice, and we will try to do some, not to say extra, but relevant to this, more practical aspects after next week. So you will be in very good shape in learning thermodynamics. So let me upload this so that the others can watch this. So next week also, as usual, we will be having the class. Okay, Bhutala, lot of things to learn. So this is a beginning, but a very solid start for you. Thanks, Bhuta. Okay. Any questions? Anything? Any comments? Even you can chat. Send in a chat. Dhananji, okay, Bhuta? Understand? Ramesh?
Yes, sir.
Okay, very good. Very good. So understanding is very important. So I try my best to make it more simple and but very thorough. So we'll proceed. Don't worry. Yeah, take it easy and have a good understanding. Yeah. So that's all for today. Then let me stop the class. Good luck to you all, and thank you for joining the class, Bhutala. Bye then. Bye for now. See you tomorrow. See you next week, Friday.